Picture this. You're cruising down the highway at 70 miles per hour, and suddenly you have to slam on the brakes. In that moment, every single microsecond counts. The ABS, the engine control unit, the wheel speed sensors, they all must communicate instantly and flawlessly. If a single message drops or gets misread, lives are quite literally at stake. Welcome, I'm your host, and today we are mastering the physics of CAN bus reliability. We're pulling directly from advanced automotive engineering texts to understand exactly how cars keep us safe right down at the physical layer.
So here's the core micro-mystery for today's explainer. How does a car actually guarantee that a critical message was received perfectly by every single node without bogging down the network with heavy software overhead? How do we achieve instant, 100% reliable data consistency on a shared copper bus?
Here is our roadmap for today. 1. The challenge. 2. ACK mechanics. 3. Dominant versus recessive. 4. Oscilloscope proof. 5. Error failsafe. And 6. Data consistency.
Section 1. The Automotive Communication Challenge.
Well, to understand how flawless communication happens, we need to look past the macro vehicle level and dive straight inside the microscopic voltage changes on the copper wires themselves. The absolute genius of the standard CAN frame is that air handling and confirmation happen entirely on layer 2, right inside the hardware controller. It doesn't wait for the software or the host microcontroller to run a check. That saves absolutely critical, life-saving processing time.
Section 2. Mechanics of the ACK field.
To see how this works, we need to navigate to the exact microsecond where the sender demands confirmation. Let's see how this builds chronologically at the end of the frame. First, the payload drops into the data field. Next, the cyclic redundancy check, or CRC, fires to mathematically verify the data's integrity. And then, we hit the critical ACK slot, followed by the ACK delimiter and the end of frame. Now, that tiny ACK slot, that is where the physical combat of the bus actually takes place.
Section 3. Dominant versus recessive bits.
Before we look at live traces, we have to establish the physical rules of the bus, the actual physics of binary conflict. I want you to remember this using the overwrite analogy. In a CAN bus network, a dominant bit, which is a logical 0, is an active overwriting state. It's exactly like a loud shout cutting through a quiet room. On the other hand, a recessive bit, a logical 1, is a passive yielding state. It's the silence. If one node whispers a recessive 1, but another node shouts a dominant 0, that dominant 0 physically overwrites the 1.
Okay, we literally cannot skip the math here because this is a physical electrical reality. The formula is delta U equals UCAN high minus UCAN low. What does that mean physically? Well, U represents the electrical potential on those physical copper wires. Delta U is the voltage differential between the CAN high line and the CAN low line. When a dominant bit hits the bus, it violently forces the CAN high line up and the CAN low line down, creating exactly a 2-volt differential. But a recessive bit? It yields. It allows both wires to return to a neutral state, meaning that differential, delta U, rests at approximately 0 volts.
Section 4. Oscilloscope proof in action.
So the crucial point is proving this math and this dominant overwrite in physical reality. When we do a forensic deconstruction of the acknowledge slot, it becomes crystal clear. The sender intentionally yields during the ACK slot by transmitting a passive recessive bit. Essentially, it's broadcasting silence. But the receivers, because they calculated a correct CRC, they shout a dominant 0. They physically force that delta U bus voltage to spike right up to that dominant 2-volt differential.
This is the overwrite in action. The sender actually physically reads the bus it just yielded. Because the voltage stays dominant, driven entirely by the receiving nodes, it mathematically and physically proves to the sender that at least one receiver correctly caught the payload. If no one received it, the bus would have just stayed at a recessive 0 volts, and the sender would instantly know it needs to try again.
Section 5. Global error signaling.
But here is the major gotcha that trips up a lot of network designs. What happens when a receiver calculates a bad CRC and needs to stop the train? It can't just quietly drop the message, right? If it did, the car's systems would fall completely out of sync. So instead of waiting for the frame to finish, the CAN protocol intentionally breaks its own rules to trigger a massive, immediate veto called an error flag. This is a brilliant brute force failsafe mechanism built right into the copper itself.
Let's walk step by step through this logical failsafe cascade. The exact microsecond one node spots a mathematical flaw, it violently blasts 6 dominant bits in a row onto the bus. Why exactly 6?
Well, the standard protocol enforces a strict bit stuffing rule that outright forbids more than 5 identical bits in a row. By aggressively blasting 6, it intentionally and unapologetically violates that rule. This forces every single other node on the network to instantly realize the frame is corrupt and trash it.
You can actually physically see this error frame immediately override the corrupted message on a raw oscilloscope trace. It's followed by a brief pause, an inner frame space, and then the sender is automatically forced to perfectly retransmit the original identifier, which in our example here is hex 113. And the crazy part? It all happens at lightning speed without the host software ever having to lift a finger.
Section 6. Guaranteeing data consistency.
Let's zoom back out for a second and look at what this micro-level combat achieves for the vehicle's macro system. This rapid-fire sequence guarantees 3 massive things. First, instant global error signaling, the absolute moment a bit goes bad. Second, immediate retransmission of the drop data. And third, culminating in the ultimate engineering prize, completely identical, pristine data across all nodes.
As our source material precisely puts it, this ensures data consistency in the cluster since all nodes only use a frame if all nodes have received it without errors. This German engineering concept of Datenkonsistenz proves that absolute reliability in a moving vehicle isn't some kind of magic. It is hardwired physics, strict math, and dominant voltage overwrites.
Understanding these physical layer failsafes is exactly what separates a barely functioning network from a truly life-saving one. So, I'll leave you with this. How will your next network design handle the worst-case edge scenario? You've got to think about the physics underlying your data. If you found this deep dive into automotive engineering valuable, hit subscribe for more EMC and automotive communication protocol survival guides. I'll see you in the next explainer.